Welcome to the 8th video on the Unit 12 playlist of our Chemistry Matters series. This video is a brief recap of the content covered in Unit 8, Thermodynamics. Thermal imaging cameras provide us with evidence that thermodynamics is the movement of thermal energy, or heat, which is usually measured in joules or calories. Heat causes atoms and molecules to gain motion or kinetic energy, which we then measure as temperature. Scientists in the field of chemical thermodynamics have observed three patterns in the movement of energy, which they refer to as the three laws of thermodynamics. The first law of thermodynamics is also called the law of conservation of energy, and it states that the amount of energy in the universe is a constant. The second law of thermodynamics states that energy always disperses, or flows, from higher concentrations to lower concentrations. This dispersed energy is called entropy, which is the measurement of energy dispersal. We also learned that Earth is an example of an open system, and fortunately, we receive a constant input of energy from the sun. The third law of thermodynamics states that the entropy of a system at absolute zero is zero. When all energy has dispersed from a molecule, the molecule stops movement and has reached its lowest possible temperature, absolute zero. Thermodynamics in chemistry is known as thermochemistry. Our students found that we can measure the energy released from or used by chemical reactions. Exothermic is a term that describes a process that produces or gives off energy to its surroundings. Endothermic describes a process that takes in or absorbs energy from its surroundings. We saw examples of these processes when exploring chemical heat packs and cold packs. Our students made graphical models of endothermic and exothermic reactions, which included a depiction of the activation energy needed to get a reaction started. Remember from Unit 2 that enthalpy, represented by H, refers to the amount of potential energy in a system. Delta H refers to the amount of heat energy transferred from reactants to products. When we explore terms like endothermic and exothermic, we're addressing a very important Georgia science standard, total bond energy. Total bond energy is all of the bond energy of the reactants after subtracting all of the bond energy of the products. It's often measured in units of kJ over mol, or kilojoules per mole. Remember that it requires energy to break bonds, and that we get energy back from bond formation. If we get more energy back from bond formation than was required to break the bonds, the reaction is exothermic. Energy is released, and the products are more stable than the reactants. If it requires more energy to break bonds than what we get back from bond formation, the reaction is endothermic. Energy is absorbed by the reaction system, and the products are less stable. The products are higher in potential energy, also known as enthalpy. Chemists refer to this as calculating total bond energy. In Unit 8, our students also observed the property of specific heat capacity in metal and plastic by comparing how ice melts on two different surfaces. Specific heat capacity is the heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Materials with high specific heat, such as plastic and water, transfer heat very slowly. Materials like metal have low specific heat capacity and are very sensitive to heat transferred, so they can feel cool to the touch, even in warm weather. Our students also completed a thorough investigation of the specific heat capacity of several atmospheric gases and found that there are gases that have a low specific heat capacity, such as methane and carbon dioxide, which change temperature readily. Another activity in our thermochemistry investigation asked students to measure heat transfer with calorimeters. We used coffee cup calorimeters to measure temperature change in chemicals dissolving in water to help us design cold packs and hot packs as part of our engineering design challenge. Using calorimeters to measure temperature change in a closed environment, calorific value of fuels can be measured. The calorific value of a fuel is the quantity of heat produced by its combustion. The most efficient fuel is the one that releases the most energy per gram of fuel. Lastly, we visited Georgia Power, a company that uses extremely precise calorimeters to measure the calorific value of coal. And we were able to explore their laboratory to investigate exactly how their calorimeters operate. Next, please join me for a recap of Unit 9, the next video on the Unit 12 playlist, where we take a look back at our unit on kinetics and gases.